conclude our conversation about mathematical induction with a cautionary tale as to why it's important that you actually do the proof of induction and not just do a bunch of cases. So for this, I want to tell you about a beautiful conjecture that's due to Poya, which goes as follows. So first of all, I have to tell you about types of numbers. So I'm going to say that a number is even type. Even type means an even number of prime factors. And so because we have even type, of course, we can have odd type. So odd type means an odd number of prime factors. So let's classify our numbers as even or odd. So let's write down the prime factorizations for some of the small numbers. So 1 is a product of 0 primes. There are no prime numbers that we put in 1, so 1 will be even. 2 is 2 times 1. 3 is also boring. 4 is our first interesting case. It's 2 times 2. 5 is 5. 6 is equal to 3 times 2. 7 is 7. 8 is equal to 2 times 2 times 2. Sorry, I was thinking ahead to 9, which is 3 times 3. You can see I'm not a number theorist. So we say because there are 0 primes in 1, so we're going to count 1 as even, 4 even, 6 even number, and because it's a 3 and a 2, right? 9 is going to be an even. And then odd. 2 is odd, 3 is odd, 5 is odd, 7, 8 is odd. 8 is odd type because it factors into a product of 3 primes. Okay? So this is what I mean by these two concepts. So then Poya counted how many numbers there are of each type. And it's nice to do this where you sort of bound how big your number is. So E of n is going to be the number of, let's say, numbers that are smaller than or equal to n of even type. And let's say I'm using green here. So O of n is going to be the same thing, k less than n, of odd type. And Poya's conjecture is for n greater than or equal to 2, he conjectured that O of n is always at least as big as E of n. And now let's look at that for a second. So we have some data here, and this is one of the things you always want to do. And in fact, Poya came up with this, maybe I can put that down, in 1919 is when he was working. And he actually checked this for n up to about 1500, I believe. So let's just compute it and make sure that we know what we're talking about here. So what's E of 6? It's going to be all the how many numbers that are 6 or less are of even type. Well, I count, if I draw my line here, I count 1, 2, 3, right? And how many are of odd type below 6? 1, 2, 3. So it's true that this one is bigger. So Poya's conjecture is true. And now if we go to 7, what's E of 7? Well, we're just going one more, it stays the same, but O of 7 got one bigger, so that one's strict. And then now it's even bigger, wow. So O of 8 goes up to 5, E of 8 is stuck down at 3, and now, of course, 9, we could keep going. So Poya checked this for n up to 1500. So it's true for n up to 1500. And you might, that's kind of impressive that he was able to do this, because remember, this is before computers. But I'm going to mention that the computer check in the 50s checked Poya's conjecture, and it found that E of n is less than or equal to O of n for all n less than or equal to 1 million. Okay, so we factored the first million numbers, and then we declared them as even type or odd type, and it turns out that Poya's conjecture is true for up to 1 million. So is there an inductive proof? Well, it kind of lends itself to that, right? Because you go up one more, so this number gets bigger or that number gets bigger, but not both. So it seems like we could be able to say something by induction. But this remained open for a long time. And then in 1962, Lehman actually came up with an explicit counterexample. Now, I don't really know how he did this, but he showed that E of n is equal to O of n plus 1 for, and now what was n? It was 906,180,359. It turns out that Lehman didn't have to go quite so far. The smallest counterexample, I think this digit becomes a 5, but it's still in the 900,000s. So Polya's conjecture has been verified by computer. It's true for the first 900 million cases, but ultimately it is false. So just doing a bunch of cases and a bunch of examples is not enough to prove something is mathematically true. That's why we take things to a higher standard in math. That's why we have to prove things, so that we know for certain they're true. If you see a pattern in going from one case to the next, that indicates that you might be able to prove something by induction. Things with prime numbers rarely get proven by induction. Things in number theory often have these sort of crazy counterexamples that happen high on, but luckily we're doing combinatorics, so lots of the things we're going to do have patterns, and induction is a powerful tool to prove that the pattern you see persists forever.